Hello, my name is John Avila to talk about deep learning for radio frequency system. Definition is a remote data storage and retrieval system that use device called DAX hard or transporters. The fundamental purpose of technology is to transmit the identity of an object using radio waves.
Let's take a closer look at the four steps involved. The first step in building a deep learning model is to access and manage your data. Using MATLAB, you can acquire signals from a variety of hardware devices. You can also generate synthetic data via simulation or use data augmentation techniques if you don't have enough data to begin with. MATLAB simplifies the process of accessing and working with signal data that is either too large to fit in memory or if you have large collections of signal data. Once the data is collected and ready, it's now time to interpret the signal data and label it. You can quickly visualize and analyze your signals using the Signal Analyzer app as a starting point. You can label signals with attributes, regions, and points of interest, and use domain specific tools to label all your signals to prepare your data for training. There are two main approaches for performing deep learning on signals. The first approach involves converting signals into time frequency representations and training custom convolutional neural networks to extract patterns directly from these representations. A time frequency representation describes how spectral components in signals evolve as a function of time. This approach enhances the patterns that may not be visible in the original signal. There are a variety of techniques for generating time frequency representations from signals and saving it as images, including spectrograms, continuous wavelet transforms or scalograms, and constant Q transforms. The second approach involves feeding signals directly into deep networks, such as LSTM networks. To make the deep network learn the patterns more quickly, you may need to reduce the signal dimensionality and variability. To do this, you have two options in MATLAB. You can manually identify and extract features from signals, or you can automatically extract features using invariant scattering convolutional networks, which provide low variance representations without losing critical information. Once you select the right approach for your signals, the next step is to train the deep networks, which can be computationally intensive and can take anywhere from hours to days. To help speed this up, MATLAB supports training on single or multiple NVIDIA GPUs on local machines or cloud-based systems. You can also visualize the training process to get a sense of the progress long before it finishes. Finally, you can automatically generate optimized CUDA code for your signal pre-processing algorithms and deep networks to perform inference on embedded GPUs. To learn more about our deep learning capabilities, check out mathworks.com. We have a large collection of examples to help you get started.
Applications. We normally refer to radio waves as the means by which radio frequencies reach communication equipment such as walkie-talkies and commercial radios. However, these waves encompass all communication devices that we have, like television, the GPS system, or mobile network. They are also present in the world of radio amateurs and any other type of element that has a wireless transmitter and receiver.
In the modern era, radio waves control everything. From the tunes in your car driving down the road to the police radio in the car that's pulling you over for not signaling your turn. These waves are undetectable and invisible to human senses, but they make up the foundation of modern connected technology. While the root of modern connected technologies may be radio waves, the underlying tech that makes radio waves possible is a rather simple concept to understand. Any person can make a simple radio in their home for a few bucks, which is part of the reason this foundational communication tech dates back to 1895. As a demonstrable introduction to understanding what radio is, we'll engage in a simple explanation of how you might make one. All you need is a battery, a coin, and an AM radio. Tune the radio to a static channel and start tapping that coin on the two terminals of the battery. You'll start hearing that tapping through the AM radio. By doing this, you'll have made a crude radio transmitter, capable of communicating in Morse code or random taps, over just a few inches though. What you're doing in this process is exciting electrons on the transmitter side, the battery and the coin, which then is received as a signal on the receiving side, the AM radio, and turned back into an audio output. What you're doing is completing a circuit between the battery terminals, which creates an electromagnetic force, which can be detected by the receiver in the AM radio. In order to understand radios in more detail than what we've just discussed, we need to take a little trip through history. Back in the early days of radio technology, in the whereabouts of the early 1900s, radio transmitters were referred to as spark coils. This was due to the fact that they create large high voltage sparks, upwards of 20 kilovolts, to send out a signal. The issue was the message was sent out on all frequencies in the radio spectrum, meaning that there was essentially only one localized channel. This was fine and dandy back in the days where no one was really using radio, but nowadays, do something like this and you'll get fined or sent to prison. These early spark coils were essentially doing the same thing as the coin and battery experiment, except at a much larger scale, meaning that they had a lot higher range. Riding the magic school bus back to the modern era, and today's radios use sine waves to transmit all sorts of information, from audio to video to raw data. By utilizing sine waves for transmission, radios and devices can distinguish different channels based on frequency, or the number of cycles in the sine wave per second. This allows tens to hundreds to thousands of channels on modern radios, all in the same space without too much interference. Every single radio has two parts, a transmitter and a receiver. The transmitter is responsible for taking a string of data and encoding it to a sine wave. After that encoding happens, it can also be amplified and sent out across the air. The receiver, rather expectedly, receives the radio waves and decodes the message encoded into the sine wave. Each side of the system uses antennas to radiate and or receive the signal. Relating radios back to your life a little bit, chances are you're watching this video as a result of a transmission of radio waves. Cell phones use radios in their most basic form. They contain both transmitters and receivers and can run both at the same time. In general, phones use frequency modulation, or FM, in a frequency range of 800 megahertz in any one of 1,600 individual frequencies. All of those numbers and data probably is meaningless to you right now, but hang on as we dive deeper. Back to our simple battery demonstration. We can recall that an electromagnetic force was created when the battery circuit was completed. Modern radios build off of this idea by creating rapidly changing electric currents on the transmitter side. One of the best way of doing this is by utilizing sine waves, as we discussed. To create a sine wave, radios use capacitors and inductors to vary the current and voltage in a controlled means. Transistors are used to amplify the signal so that it has a further range. The problem, though, as you might have picked up, is that sine waves don't natively carry any information. They provide a foundation for transmitting information, like the Oreo cookie is the transmitter for that delicious filling, or like crackers are the foundations to that dry-aged Gouda. You get the point. In order to get sine waves to actually carry information, you need to modulate it. You can do this in three ways: pulse modulation, amplitude modulation, and frequency modulation. Pulse modulation means that you turn the sine wave on and off, just like the IT guy suggested. Doing this allows you to easily send Morse code, but that's just about it. Pulse modulation is rarely used except to control clocks across the US. The simplicity of pulse modulation also allows one pulse modulator to cover massive areas, like the entire US. Amplitude modulation, on the other hand, is what is utilized by AM radio stations and TV signals to encode data. In this format, the amplitude, or peak-to-peak voltage of the wave, is changed. You can imagine this as the wave from a person's voice being combined with a sine wave to create a new, rather complex sine wave with the same frequency, but with a lot more data inside. Finally, frequency modulation, otherwise known as FM, is used for FM radio and tons of other wireless tech. In this encoding technique, the sine wave frequency changes slightly based on the signal. This means that the distance between the peaks of the waves is varied based on the data that's trying to be transmitted. Bringing all of these different techniques back into the real world, we can begin to understand them a little further. If you sit in your car and tune your radio to AM 680, that means that the transmitting station was operating at 680,000 hertz, meaning that the sine wave repeats 680,000 times per second. The voice of the speaker or the music on the transmitting side is modulated onto that wave through amplitude modulation. Then the signal is amplified up to 50,000 watts for larger AM radio stations and then sent into space utilizing the antenna. Your car's radio picks up that signal, utilizing its own antenna. This can be as simple as a wire or a metal stick. In conjunction with the tuner on your radio tuning to the specific frequency, the tuner starts resonating at 680 kilohertz. Called resonance, this principle allows the radio to essentially ignore any other signals in the air. The signal then passes to the detector, or demodulator, that takes the voice or music from the wave, utilizing a device called a diode, and translates it back into audio. The final step in the process is for the radio to amplify the signal so you can hear it and change the volume as needed. FM radios have different detector setups and translate frequency into sound rather than amplitude, but otherwise they operate in the same way. Data can be encoded onto a constantly changing signal utilizing different modulation techniques that have advantages and disadvantages to each method. Nearly everything that communicates wirelessly around us uses radio waves to do so, and creating your own simple radio is actually a very manageable task. Over the last century, radio has radically changed the course of humanity and rapidly accelerated the growth of the information age.
Pros and cons. Pros. Versatility. In terms of the terrain that radio communication can cover. Cost savings is also a fact to take into account since a large investment in material is not necessary to support communication in a large area. Great frequency and reliability of data collection. Cons. As with virtual and wireless communication, availability can be a huge problem if mitigating factors and potential situations are not taken into account where malicious users may use different techniques to modify or inhibit communication.
So I'm pleased to introduce and talk about the RFS microwave antenna product line. The latest development for the industry, and I'm pleased to say that RFS are well ahead of the game, relate to so-called dual band antennas. So basically we take a low band antenna, let's say at 15 gigahertz, and we combine it with an 80 gigahertz antenna. So essentially there's a 15 gigahertz and an 80 gigahertz radio transmitting simultaneously. And this does two things. It allows the link length to be extended. It keeps the availability high. And generally the throughput through that system can really go into the gigabit range. RFS have developed this range of products. They are compatible with the current OEM radio interfaces. I said they're rugged, they are. I said they're compliant, they are. And actually the volume levels that RFS are capable of are extremely high. So manufactured in Europe, great reputation. Of course, you can ask any of my RFS colleagues for details on these products, and we'd be very glad to give you those details. Thank you.
Radiofrequência in Ecuador is sometimes very important used in industries and communication networks. Conclusion. In conclusion, there are many other uses for this wave. It is applied in industries such as metal, food, or astronomy. Experts in mobile communication and other fields continue to research and discover new ways of use. So we can make a complete list of all the applications that they have. It is probably an exhaustible source of stage and technology development for this and for new application in the future. Sometimes that is now strange because after all radio waves surround use and are present throughout our universe. Thank you.